Hello, Internet. We are live.
Hey everyone, welcome to episode 57 of the Stanford MLSys seminar series. I'm Kran. As always, we have with us Fyodor
Hey.
and
Hey.
Euro, and our guest today, Vijay Reddi from Harvard. So as always, we're going to have a 30-minute talk followed by a 30-minute podcast style discussion where you, the live audience, can ask questions. During the talk, you can keep those questions coming in chat. And we'll try to get those across to Vijay during the podcast portion. And you can keep the chat lively, of course, with comments and stuff. A little bit about our speaker today. So Vijay is going to be telling us a little bit about tiny machine learning. And we've had a talk in the past actually from Pete Borden about this. So very excited to hear Vijay's perspective on this as well. Vijay is an associate professor at Harvard, also VP founding member of ML Commons, as well as serving on the ML Commons Board of Directors and co-chair of the ML Commons Research organization. Also co-led the ML benchmark and has received a lot of awards from many different organizations, including the National Academy of Engineering. So with that, I just want to hand it over to Vijay. Take it away.
Awesome. Thank you, folks. It's a pleasure being down here. So today I'm going to talk about what is tiny machine learning. Folks might have heard about it. I'm going to give my own sort of spiel around what TinyML is, why it's exciting, and what are some of the challenges and opportunities that are broadly in this space. So with that said, let me just kind of start with the definition of what is tiny machine learning so that we're all kind of calibrated to be on the same page. Broadly, I'd say that TinyML is effectively a fast-growing field of machine learning. And the beautiful thing about this is that it's really about the intersection of machine learning algorithms and embedded hardware and embedded software. Now, that sort of marriage between embedded hardware and embedded software and machine learning algorithms is really where I think a lot of the unique challenges and opportunities actually come about. A lot of people know ML, a lot of people know about systems, but talking about embedded ML and systems is a whole different beast. And one of the intents of this talk is to kind of give you a little bit of a sampling of some of those technological sort of hardships that people face when they're trying to actually deploy these models. But before I get there, let's kind of get a little psyched up about what are some possibilities, right? The whole reason that we're all excited about TinyML at large in the industry and academia is fundamentally because you really want to be able to do ML very close to the sensor. Now, sensors generate an insane amount of data. The amount of telemetry data and so forth that's coming, be it from satellites or be it from your everyday devices that are all around you, is huge. What this means is that if you can convert a lot of that data that's actually kind of streaming by into some sort of information or knowledge effectively by running ML, then you can extract a lot of insights. Now, one of the key things about doing on-device sensor analytics rather than taking the data from the sensors on any device and beaming it up to like the big ML services is really that data movement is really going to kill you, because that's first and foremost, it's going to be an insane amount of bandwidth. It's going to kill you in terms of your latency. It's going to hard to get reliability in that because you have communication channels involved. Then, of course, there's energy efficiency. Any oxymoronic person knows that communication is ridiculously more expensive than actually doing computation. Computation is dirt cheap. So rather than move the data over to where the compute is, the whole intent is pretty simple, right? What you want to do is you want to take that ML, the computational capabilities, and move that over to where the data is, because that way you can be much more efficient. And of course, the killer, I think, use case is really going to be around privacy-related aspects, because you're talking about sensors that are collecting a lot of data. And more often than not, a lot of these sensors can also be around us, which means privacy becomes a pretty critical thing. And the whole intent behind TinyML is really that you want to do this with ultra low power consumption, because you're doing ML that is continuously running, always on. And in an ideal world, the way TinyML would differentiate itself from traditional big ML, mobile ML, and so forth, is that it's really going to be operating on battery power devices. So just to kind of put the whole thing in context, right? So traditionally we used to Cloud ML. Cloud ML is increasingly been moving on to on-premise and gateway-based servers or edge computing servers. Then it's moved down to mobile. And I think like the really exciting space right now is in the ultra low power domain, where we're talking about maybe 100 milliwatts of power, battery power devices, and so forth. And how do we run, TinyML in this? That's effectively what TinyML is, and how do we run things around this space? The most common use case of this is really around the consumer applications that you and I pretty much take for granted. For example, when you say, okay, Google, hey, Siri, and so forth, these machines wake up. How do they wake up? How are they always on listening, right? So that's an example where you actually have a wake word detector that is running effectively on some sort of low power DSP or low power microcontroller that's able to detect that sort of a keyword and then trigger the rest of the pipeline for ASR. And increasingly what we're starting to see is that we're seeing more and more endpoint devices that are starting to use ML in some capacity. The Apple Watch is a classic example, but more and more we're starting to see the pervasiveness of the technology. And one would expect that by and large, I'd say in another handful of years, you'll see a lot of devices, practically any device that's around us has got some kind of sensors that's doing some sort of data analytics on us continuously. Now, I think there's some really interesting applications and use cases. I'm going to skip playing the videos in the interest of time, though. But fundamentally, what I wanted to show is that, like in these kinds of small little nano drones, you can actually have really powerful applications. In search and rescue and so forth, these kinds of consumer drones are actually quite powerful. They often tend to have only about like tens of kilobytes or hundreds of kilobytes of SRAM or flash, which is extremely resource constrained. But nonetheless, if you could imagine that you can have TinyML models that are running on these devices where you're able to do object avoidance and being still able to do things like source seeking, for instance, then that enables a lot of really killer application use cases that are well beyond the consumer electronic sort of devices that we're typically used to. I'm going to jump real quick into the next one. And one of the latest things that's actually happening, and some things we're dabbling around space sats is like for CubeSats, is really looking at applications of TinyML up in space. And one of the reasons that we want to do this is because typically when you're looking at CubeSats and so forth, they're really constrained for bandwidth, latency, power consumption, and so forth. And so one of the things that happens here is that they struggle with actually processing data on board. And if you can actually have a lot of low power embedded ML on those sats, you can actually make them far more intelligent. And I'm just showing you a picture of a Sony microcontroller that was actually put up just recently up in space for some undisclosed sort of a use case. What I'm really trying to get to is the point that there are lots of really interesting applications that are on the horizon, right? So looking at like search and rescue drones that are in like extremely small form factor, having CubeSats actually using ML on board with ultra low power consumption. Those are sort of like some of the interesting frontiers where you can actually enable really rich use cases. And ultimately, in the context of TinyML, it all boils down to just dealing with sensors, right? There's sensors everywhere. If you kind of look at any given system that is out there, most of the vehicles, robots, all of them are dealing with sensor data, motion data, acoustics data, environmental data, image data, and so forth. And so if you can actually tap into the capabilities of being able to put ML right next to that sensor, you can really take a lot of the raw data that's coming through at a really high bandwidth and convert that to intelligence. Just a quick interesting stat is that, like, if you kind of look at a lot of the IoT devices are mostly around sensors, right? They produce around 5 quintillion bytes of data, which is freaking mind-boggling. Because if you look at the amount of data that we're actually harnessing today, it's a tiny fraction of the amount of data that these small little devices that we take for granted can actually produce. So in effect, even though they're producing lots of little data, all of that data really translates to huge big data problems. What classically means is that this maps real well to traditional ML or deep learning based methods. Now, there are lots of different things I can talk about in the context of TinyML. I mean, there is so much work that is actually happening at large. But in this particular talk, I'm going to try and just cherry pick some key areas. So first and foremost, I'll talk about some of the challenges around how do you deploy machine learning on embedded devices. A lot of people think, oh yeah, I know how to build models, I know how to deploy things. Yep, that's one thing when you talk about non-embedded systems versus when you actually talk about embedded systems. That's where when the pedal meets the metal, it becomes really quite complicated to get these models to run. Specifically, I'm going to talk about what it means to get a machine learning model to run on embedded ecosystem, not a single device, right? So for example, I can get a model running on one device, but getting it to run on multiple devices, that just changes the landscape quite dramatically. And that's really where some of the fundamental technological problems are. Then next, I'll move on to talking a little bit about data sets, because I think data is obviously, as we all know, data is sort of king in the machine learning space. And I want to talk about how we need to be looking at data. Again, I'll talk about this in the context of TinyML use cases. Third, I'll touch real lightly, as I go towards the end, I'm going to start giving less and less info. I'll talk about some of the hardware design space exploration, sort of like talking about it from the software or the data sets down to sort of how do you do acceleration, what sort of frameworks are there, and so forth. And finally, I'll talk about how do we disseminate information from sitting in the ivory tower over to just making this information and knowledge accessible broadly at a planetary level, right, in terms of education and outreach. So let me start off by talking about the first point. There are about 250 billion microcontrollers today, which is awesome. What this means is that the ecosystem for being able to enable intelligence on a lot of devices fundamentally exists. It's not like I'm talking about, let's go out and build some wicked little widget and then let's try and sell this and convince everybody on the planet that we're actually going to be able to deploy this at scale. What I'm saying is a lot of the computational horsepower that we need, the sensors and the computing capability next to the sensors effectively exists today already in the ecosystem. Now, they come in many forms and many form factors, and these are just example of development boards I'm showing you. But the fundamental point I'm trying to get to is there are lots of these different devices that are out there in that 250 billion. One of the challenges that you very quickly run into in this ecosystem is that these devices tend to be highly specialized. Often when you're talking about embedded devices, they'll come with different clock frequencies, they'll have different sort of memory capabilities in terms of the amount of flash they have or storage, or the amount of SRAM they have on board. They also tend to come with a variety of different sensors, and some have communication, some don't have communication. The reason I'm harping about this is that this actually becomes a serious problem when you're trying to deploy machine learning at scale on embedded devices. Typically, if I said Windows, Linux, iOS, Android, well, by and large, I've probably covered most of the ecosystem for computing already, right? But when you look at the embedded ecosystem, it's not so homogeneous enough in a way, right? The Android ecosystem, for instance, you have 4 billion of those devices running Android in some capacity. By and large, that tends to have a standard sort of interface and whatnot. But if you unravel this hardware ecosystem, it starts presenting new challenges. So the challenges at large can largely be broken down into hardware and software, right? On the hardware side, for instance, because you're looking at embedded systems where low power consumption is fundamentally in like a requirement, what you end up with is a lot of devices that are highly specialized, right? They tend to be highly heterogeneous because the only way you really get specialization is really by having extreme heterogeneity in the ecosystem. Because given a particular use case, you're going to have to try and target that use case rather than build a general purpose system. Therefore, you end up with a lot of these embedded devices that tend to have different kinds of microcontrollers, like even, if you look at the ARM class microcontrollers, you might have Cortex M0, M4, and whatnot. Some might have an FPU, some might not have an FPU, some might have SIMD support, some might not have SIMD support. What this means is that now when I build a model and I want to run it efficiently, it might run real well on a single device, but there is no guarantee that that exact same code base would actually run pretty well on another device. Now, these are kind of challenges you and I would typically not be dealing with if we're running them largely on big fat GPUs or big fat TPUs or CPUs and so forth. So that heterogeneity becomes a serious problem, especially at the instruction set architecture level. It gets really hairy because even within families of the same ecosystem, like for example, if you take Tensilicas or DSPs, even within that sort of family, you will have really fragmented ISAs. What that means is, again, you get code that is compiled down for a particular microcontroller, so it inherently becomes, there's no portability. Another thing, of course, these are just embedded devices. As I showed you, you tend to have like about 256 kilobytes of RAM or maybe 512 kilobytes of RAM, which is really small. And that becomes a real limiting factor in terms of your weights and managing all your intermediate values that are actually being computed upon as the model is running. And power, of course, is extremely critical, right? The other side of the world is really about the software. Typically, when you're building, when you're writing code, be it in PyTorch, TensorFlow, and so forth on a traditional system, you take a lot of things for granted. So, for example, very simple things like, doing memory allocation. You don't sweat it, right? There's a malloc library or something that you would use. When you look at the embedded ecosystem, you cannot be guaranteed that you're going to have homogeneous sort of library support across a range of different devices. What this again locks you means is if you pick a device, be careful if you start becoming dependent on the device's characteristics. You can get into a pickle because that code is no longer portable. Of course, this notion of having an operating system is a pie in the sky sort of a dream in the embedded system because you don't generally have nice embedded systems that are homogeneously deployed, right? Like in traditional systems, you might have Windows, you might have Linux, and so forth. And by and large, you can take programs that are working on one machine and drop it onto another Linux machine, and it'll be fine. But that sort of a guarantee doesn't actually exist. And that's really where, the whole TensorFlow Lite Micro, which actually Pete, was one of the drivers behind, along with, a big team and myself included. One of the key goals was actually trying to build an inference engine that would actually be portable across all of these kinds of challenges that I just discussed. I'm not going to go into a lot of technical details. You are welcome to ask me questions about this, and I'll explain, how the system internally works. But the key essence of TensorFlow-like Micro is that when you look at an embedded system, rather than compiling code down to a particular microcontroller, the intent behind TensorFlow-like Micro is that you actually use an interpreter-based design. Now, typically, you would not want to use interpreters when you're building any sort of a system because interpreters are inherently slow. Python is about 70x inefficient compared to C and C++. We all know this. So why in the heck would you actually go and build an interpreter rather than build something that's a compiled system? Well, the reason is because interpreters allow you to have portability, right? And one of the beautiful things about having an interpreter-based design for machine learning systems specifically is that every instruction when you're interpreting is actually going to be executing for millions of instructions. Now, this is counterintuitive to what a traditional interpreter would do. For example, if we were to take Python and you're looking at a single statement that you have to interpret, well, that overhead of the, reading that particular statement and then actually doing the decode and the dispatch and all of that overhead actually ends up being quite substantial per instruction level. Well, in the case of ML graphs, you're looking at a convolutional operator and you say, okay, I want to run a con, right? Well, okay, well, that's a pretty hefty operation where you're going to spend millions of cycles. The overhead of doing these kinds of traditional interpreter dispatch loop and so forth is very small. So that's the fundamental nugget behind how you can actually achieve portability across embedded systems. Happy to go much more into details later. But the key nuggets is that it's got a very small footprint. You don't rely on any dynamic memory allocation. Embedded system engineers absolutely hate any kind of memory fragmentations that might show up because of any kind of dynamic memory allocation. So you don't want to have any kind of that sort of dependency. Same, as I alluded to earlier, you cannot assume standard libraries will actually exist on different embedded systems. Otherwise, you lose portability. Same thing, you cannot assume that you're going to have operating system level sort of support, right? Because you got to be able to run bare metal. And the whole nugget behind the interpreter-based design with these principles in place is really that you want to get portability across different types of devices. So that's one of the key nuggets that I actually wanted to touch on, because more often than not, I see really cute papers that come out which talk about, hey, it's like, we specialize this sort of an interpreter and get like this sort of a compiler and it works on this particular device and check out my super awesome result. And I actually say, well, yeah, that's great, but in practice, that's not really going to be useful because you can't handle the scale at which the embedded ecosystem exists at, right? If you really want to solve and make a dent in this space, what you really got to do is try and head on address the problem. And this is one of the approaches, but there are many other papers that are starting to kind of wrangle their head around the fact that this is an extremely heterogeneous system. All right, so I kind of just harped around the endpoint around how you deploy models and so forth, right? Like that's sort of the tail end. But in this machine learning workflow, one of the things that I really want to focus on really is like how you deal with the issue of data, right? And I'm going to talk about this specifically in the context of a TinyML use case, the very cookie cutter use case, which is keyword spotting. When you say a word, it either recognizes and does an action or just ignores it. What I want to talk about here is really how do you enable keyword spotting as an application for all the different languages that are out there. If you kind of look at, if you look at a Google Assistant, you look at Amazon Alexa and so forth, you can literally count a handful of languages that these amazing virtual assistants support. So what's that to say? Is that to say that the rest of the languages, we just don't care? We just have large data sets for English, Spanish, and so forth. So the rest of the people, adios. What you really want to do is find a way that we can actually support a large ecosystem of different languages and make that really easy, right? And so that's the key question that we're wanting to address. One of the challenges, obviously, once you try and address a challenge like that, is the fact that the volume of data that you really have to train ML models diminishes real fast as you try and tackle the long tail of different languages that are spoken by the many people that are out there. And by the way, there are over 7,000 different languages on this planet, right? And no one language, for me at least, is any less important than English or anything else, right? For me, it's about equity in the system. So you got to treat all of these languages with fair capabilities. So typically, what do? Typically, what we do is we tend to have, static data sets. We go out, we go through all the effort of, collecting the data, labeling the data, checking the data. We do this either manually or we come up with fancy tools like Snorkel and all those things that exist, which do amazing work in terms of being able to, shrink that time to create the data set. However, here's the thing. I still feel like the way we are looking at data is inherently static. we tend to think of like data sets. We create data sets and then, okay, I'm going to train a model, right? I don't like thinking about data sets in that way. I like to think about data sets as being live. The example that I like to use often is that, like, if you look at Google, for instance, right? Google effectively has an enormous data set into which they'll peek in and then they'll be able to pull, they'll be able to find a needle in a haystack. It's pretty amazing. So for me, what they've really done is not that they have indexed the data. What I find fascinating is how you build a system that can handle the large volume of data. And it's that computer architecture, that overall computing system architecture, that's really fascinating, right? Which is being able to go out and find, building the computing system that I can actually dig through that volume of data that's out there and then figure out what are the top 10 results or whatnot that you want. Now, in a similar way, I like to think about how can we enable interesting data, like data set generation, given a particular task you might have at hand. So let's say hypothetically, for instance, I want a TinyML model that can recognize a handful of words. Now, what I don't want to do is go out and build manually, go and get this data. Instead, what I effectively want to do is, like, I want to imagine that I have this input of set of words and out comes a model. And the rest is not my problem. The rest is just an automated pipeline. In other words, there's no manual data collection. There's no manually sort of tweaking things around, right, to get that data set. How could we potentially go about doing that? And I'm going to talk about this automatic keyword dataset generation tool that we built. The intent is this. So you specify a handful of words, and there are lots of open corpuses out there with transcribed speech where you can actually go and find sentences where this speech actually contains the critical word segments that you care about. So for example, there's the first one here has the word up. He gazed up at the steep bank, right? And what you want to do is then extract those kind of keywords on the fly as you need them, and do this on, for whatever set of keywords you have, and then be able to dynamically kind of extract that out and then effectively dynamically create that data set that you need, which can then be used to train whatever model you want, right? Now, this is what we actually put together, and this is a New York's paper that just came out like last year, where the challenge we were going after was really trying to cater for a wide number of different languages and to enable, virtual assistant kind of capabilities on them. So we start off with the challenge of like doing this for 50 different languages. And what the multilingual spoken words corpus does is exactly that pipeline that I showed you. And what it ends up creating is this massive corpus of over 340,000 keywords, right? And it's all automatically generated. In comparison, Pete's actually one of the authors on this thing, because one of the things that Pete had done was he manually created the TinyML, Google speech commands data set, which took an insane amount of effort, and it took a long time for him to even be able to update it, versus being able to use, an automated data generation pipeline, right? And so by doing this, in many ways, what we were actually able to do is we're, for the first time, able to create new data sets for languages that never had a data set before. What this means is that you're unlocking, or you're really democratizing this kind of a technology for many different low resource languages. Okay? Now, there are many more languages. I said earlier that there were 7,000 languages on this planet. How can you handle them all? Well, I'm not saying we solved the entire problem, but one of the key goals that we were going after was, can we build enough of this technology so that we can actually have an automated pipeline to be able to reach that goal of supporting many diverse languages. And I'm showing you down here, for those 50 languages, that the corpus is not evenly balanced, right? So there's some languages where we have very few unique keywords in there, and we have few audio clips and whatnot. But nonetheless, this is still a step forward in being able to support keyword spotting, as an example, on many different languages. So in this interspeech paper, for instance, what we did was we actually took languages where we had a good amount of corpus, and we trained an embedding representation, right? Which can then later be used with few-shot keyword spotting sort of training, where you just give it a handful of examples, like about 5 examples, and then you can really quickly get a model trained even for low resource languages, which is kind of cool, because now this means that you don't always have to have large volume of data in terms of bringing equity, in terms of supporting all kinds of different languages. Just a quick chart here saying that, obviously you can train a model, you train the embedding model with languages for which you have seen the data for before, right? And then this is the more interesting results, where now we suddenly start throwing languages that it's actually not seen before, right? And you're still able to get fairly good sort of accuracy in terms of, keyword spotting. So the point that I'm trying to make here with the data set point is to actually think about how can we think of data sets as live data sets rather than thinking them of like static data sets, and what kind of technologies can we put in place so we can unlock new capabilities. As I said earlier, I wanted to touch on 4 things, which was sort of talking about dealing with the embedded ecosystem's heterogeneity, talking about the data set aspect and how do we support more that, bring equity in the system by supporting many different kinds of languages, and what do we do for that. And the third one was about like, hey, what can we do at the lowest levels of the hardware stack? So CFU Playground is, again, in the context of TinyML, it's sort of like this design space exploration that you can do at the architecture/microarchitecture level. Typically, when you're dealing with machine learning and you want to accelerate it, the very first thing that people will do is like, okay, let me go build a small little widget, right? My accelerator little widget. And then, that'll be my accelerator that this CPU will offload the computation to. This is, how we do things with GPUs. This is how we do things with CPUs and so forth. But the problem with doing that in TinyML really is the fact that that dramatically increases the cost, because now you have to have a dedicated accelerator that's going to be sitting on, your platform next to the microcontroller, which also means it increases the size and so forth. We're talking about TinyML. So clearly these are things that go completely polar opposite in the direction of TinyML. So what we're interested in actually doing is looking at taking an MCU, and rather than kind of pairing it with a beefy accelerator, can we progressively kind of expand that microcontroller so that you can dynamically decide, not dynamically, you can effectively decide at design time, just what's the right balance of how many resources you allocate to the microcontroller versus how much you actually allocate to the accelerator. And the accelerator is effectively coupled tightly into the data path of the processor. So therefore, the latency and so forth is really very negligible in terms of invoking the specialized unit. There's a huge design space that can be explored, and CFU Playground allows us to kind of do that sort of design space exploration. And that's the point I'm getting to. The last point I kind of want to say is one of the key things that I'm really passionate about, and I would like to see more of us actually being focused on, is really how do we bring about equity when it comes to machine learning technologies. What I mean by that is kind of thinking about how do we actually enable machine learning to be globally accessible, right? Often, a lot of people, when they're experiencing or learning about machine learning technologies, it ends up being that they're dabbling with some sort of a computer screen, and they're programming these models that are looking at ImageNet data or whatnot. But it's very hard to kind of close the loop where you actually deploy the model into practice and then experience how it works. However, when you're dealing with TinyML and you're deploying things onto these small little embedded devices, it's a beautiful vessel to actually be able to help people and students understand machine learning, specifically applied machine learning, because you can actually take these models, deploy them, and close the feedback loop where you can actually try it out, right? So students can actually try it out. They get like a direct feel to how the model works or does not work. And then that way they can have a deeper appreciation for the most important part of the ML pipeline, right? Which is actually the data collection and so forth. That is often the part that I think we don't emphasize enough when we're talking about machine learning at large. We tend to focus a lot about the exciting space around models and so forth, when we know the data is really the thing that people really need to have a lot of deep appreciation for. So in this widening access to applied machine learning paper, we actually talk a lot about this sort of a closed loop mechanism that TinyML enables and how it's useful for actually helping people learn more about ML and do so much more effectively. So I know you've got 30 minutes, so I kind of wanted to bring you back up because I know I touched a lot of things, but let me kind of quickly summarize. First thing I wanted you to understand is that deploying models in the embedded ecosystem is not as simple as deploying them in cloud-based services where you tend to have push button things. The reason is because the embedded ecosystem is highly fragmented and you have to have a deep appreciation for it. Otherwise, you will never really reach the potential of what TinyML is. And unless you understand that and think about it very carefully, you won't be able to scale it out. The next thing I'm talking about is around data, and specifically the question around, rather than thinking of data as static, I think it's really interesting to think of data as a continuous live stream that you're actually tapping into. Third part, which I talked really lightly about, is that when you're designing microarchitectures, you don't have to think of microarchitectures as being like, okay, I have an accelerator for my machine learning, and then I have my, Mickey Mouse CPU. Rather, you can think of them as being fused together. And if you have the right platform to be able to do that sort of a design space study, you will be able to naturally kind of build, you'd be able to tap into a new area of the microarchitecture design space exploration. Last but not least, I'm really passionate about education and outreach, and I think increasingly more of us should really be doing this rather than always thinking about cutting edge stuff. We already do cutting edge stuff all the time, but I think it's very important, especially with these kinds of technologies, that we bring equity in the system and make it globally accessible for people. With that said, I'm going to turn it back to you all. Thank you.
Thanks so much, Vijay. That was a great talk. Covered a lot of different topics in TinyML. So I'm hoping we'll have a bunch of interesting questions. Quick reminder to folks on YouTube, please put your questions in chat, and we'll get those across to Vijay. I guess to kick things off, maybe a slightly more technical question. I guess you talked a little bit about TensorFlow like micro and specifically, I think kind of this idea of using an interpreter-based approach. I think one of the things that I maybe didn't fully understand was what makes that approach more portable compared to doing, let's say, a compiler style approach for the models. And the second question, maybe part two, is sort of like, I assume that there are restrictions in terms of just what kind of models can be supported. So I'm just curious, what is the breadth of models that you can actually deploy on devices, and kind of how does that impact, performance in general?
Yeah, it's two questions. So one is about portability. Yeah, so I'm glad you kind of asked that question because it's one that takes a little bit of explanation. So the first thing is that, like, when you deploy models onto an embedded device, right? Normally what you would do is you would actually have to compile it down and through the tool chain. The second you compile it down, what does that mean? How do I update this model, right? There's no chance of updating the model. I mean, not a lot of systems don't actually support over-the-air updates, right? So that becomes a serious sort of a problem. Now, if you use an interpreter-based approach, what that means is that you would keep the model as data effectively, right? And therefore, you can actually do over-the-air updates if needed. In other words, you would actually be able to, update the model while it's already deployed someplace in the wild. That's sort of a key nugget. Another thing that's actually quite important that a lot of people don't realize is that you obviously want high performance kernels, right? When you're running something on any device, embedded device or otherwise, right? You want high performance. How do you get high performance? Well, you have to have optimized kernels. It's exactly what NVIDIA does. When you run it on them, if you use, the TensorRT, you get really high performance kernels. Okay, well, the same thing is something that you really want on the embedded system. Now, in the embedded ecosystem, I made this big case that it's a hodgepodge mess of different kinds of microcontrollers from many different vendors. So does this mean that, for example, be it the STM, be it like the TensorFlow Micro or PyTorch embedded, are they going to provide, is the expectation that these operators that are there are going to be highly optimized for this broad ecosystem? There is no way in the world that an ML framework team would ever be able to provide a high performance kernel for the broad ecosystem, right? This is one of the big challenges that the TensorFlow Lite Micro team faced. But then if you have, one of the key ways you can address that is by having a decoupling where you allow the interpreter-based system to kind of pick up just the operators it needs, right? And you can do that by having individual hardware vendors provide the specialized kernels, which the interpreter can actually latch into and do the dispatch to, right? That is extremely key. And this is a sort of a nuance, but a very critical point that a lot of people don't appreciate as compared to traditional systems. And that's because in traditional systems, we don't have the extreme level of heterogeneity that we have here. Okay? So that's about the portability. And the second thing you were asking about was around models, what kind of models you can support. Now remember, first and foremost, these models have to be extremely small. Just today, I was talking to a company that was talking about how they had deployed some sort of really creative touch interface on a very large smartphone manufacturer, like, device manufacturer. And they were told basically that you only have 30 kilobytes that you can actually get access to, right? And so obviously that means it's going to be highly restrictive in terms of the types of models we're talking about, right? Now, that said, I think for now, everybody's still kind of using autoencoders, or everybody's using basically CNNs to do most of the work, or traditional MLPs. A lot of people often ask me about, like, well, are we going to get recurrent characteristics or not? I think it's a bit of a chicken and an egg. framework engineers don't want to implement this until some app people actually show that it's actually useful, some interesting for some reason. So I think like this field is still evolving, and it's like you're building the bridge as you're trying to cross over. So it's kind of hard to say that, oh yeah, like certain network types or certain primitives are not important. Does that answer the question, Karen?
Yeah, I think that's a great answer. A quick, I guess, follow up. One of the things I was wondering as you were talking about data specifically was, like in the keyword spotting case, and I've actually used Google Speech Trends, it's great. But in the keyword spotting case, like one of the things that's interesting is that you can actually gather that data without necessarily deploying the sensor in the wild, right? Like you can use a microphone to record someone saying these keywords, or as you did in your work, like you can also extract it from just speech or audio that you might have lying around. But a lot of like the use cases you talked about at the beginning are these kind of interesting like cases where you have like sensors in the wild collecting data, and in those cases, you can't get the data from anywhere except those sensors. So I'm wondering, like, how do you kind of close the loop in this general kind of framework where you connect the data to the model builders and then kind of circle back to deploy the model on device? Like that piece seemed like it might be tricky just because you have to gather all this kind of large amounts of data and then ship it to someone to actually do model building.
Yeah, this is a really hard problem. It's really interesting because a lot of companies have a lot of data, incredibly, in sensors. I mean, the wildlife and so forth, that's a different thing. I'll address that. But when it comes to applications and manufacturing and so forth, there's definitely a lot of data that's around. Now, the key challenge, though, is that how do you get this data to be accessible to people who are not within the company, right? And I think this is one of those things. I can tell you, for example, we have a grant from NSF, which has got to do about smart manufacturing, right? Basically, you want to do next generation manufacturing plans, and TinyML is a very critical part of it because you want to do predictive maintenance and all that. For large companies, who have the bandwidth and the capabilities to create MLOps teams that can actually support it, that's a different case. But for manufacturing, especially if we want to bring the US back up to the grade that the government wants to have it at, right, competitively, then you find that there are a lot of SMEs, like small to medium size, manufacturing lines, that actually don't have the ability to try and come up with creative models and all this stuff. And the fact that they realize that there's a need for this kind of a capability, and they realize that, oh, we are sitting on data, but the data is actually not being made available to academics and researchers at large, has led to this discussion about them actually coming together and saying, yes, we can let you have the data, right? So I think that's kind of effectively, it's a bit of a manual process, but what we're starting to see is that industry is starting to pool its data together because they want the solutions, but they are also sitting on the data. And without the data, we're like, you can't have solutions, right? So I think that's a bit of a movement that's kind of happening in that sort of space. When it comes to the wildlife stuff, it's really hard. I mean, there are ways you can, quote unquote, get that kind of data from existing sources, but you're right, it doesn't really work because, yeah, the sound is just inherently different. I mean, you and I might not be able to pick it up, but the machine can clearly tell it's a different sound. I don't really have an answer for that, because that definitely seems like a manual and tedious process. I recently had a student who had taken my online courses, and when I was finally happy that was able to do stuff, but then he was so frustrated. He was like, wait, this means that because everything is so tied to the sensor and so forth, I have to like physically be there and collect that exact bit of data, and like, how is that going to work? That goes back to your exact question. And I think it's something that I don't have an answer for it clearly in my head, and I haven't heard anyone say like, yeah, this is how to do, deal with that problem.
Awesome. Thanks so much for the detailed answers. I'm going to hand over to Dan now.
Well, Vijay, one of the ideas that I think was really compelling to me in your talk was the idea that data is actually live and that it's not static. And I think that's, something that's really fundamental and is probably a major challenge for kind of any ML system these days. Have you had any thoughts about how to extend some of your techniques or some of your ideas to more general settings or to other domains? We hear about distribution shift a lot in vision and places, self-driving, that the season changes and then all your models get messed up. Have you thought about kind of extending some of those techniques to other modalities and domains like that?
thought about it, but have we done it? Not yet, because in fact, as I just kind of pointed out, right, that work just kind of came out. And in fact, Mark and Kobe, who actually led a lot of that work, are actually now trying something similar for the visual domain, instead of sound. And I think increasingly people will kind of latch on to this sort of an idea. But I think like what's interesting is what are the tools and pipelines that we need to put in place that will actually allow us to kind of explore this? I think is really interesting. So yeah, short answer is no, we haven't done the work yet, but yes, we have thought about it.
Cool. Go ahead, Piero.
Yeah, I have a follow-up on that, which I'm really curious about, and is if you start from this assumption, right, that the data is live, then I guess there is also a matter of interaction and let's say collection of those data that is also kind of interactive with the user, right? I'm curious of your take on this aspect, and I'm not talking directly about active learning, but also more in the sense of actually closer to what some of the work that Dan did in the recent past about updating models and learning with them in a interactive way.
Yeah, I don't know about the interactivity kind of angle in this particular context, right? Because yeah, often these devices are kind of like just slapped someplace, someplace crazy, and I mean, in most cases. So I think it's probably going to lag behind in that sort of a perspective, because it's hard to kind of have a closed feedback loop. I think this always goes back to that point, right? It's very hard to close the loop with these things. It's very easy to do this forward pass of kind of in the MLOps kind of style, right? Where you actually have stuff and move it all the way out and deploy it. And I think the biggest problem that we have really here is that the continuous monitoring stage at the end of the pipe, and being able to use that to close the loop is, I think, what the Achilles heel of TinyML is.
Yeah, that's
around models. I think that is the fundamental thing that's going to be the killer. I mean, I say this all the time. It's like, when we all talk about IoT, I think I don't know where we came up with this Internet of Things. It just kind of doesn't make sense. I'm like, these are things. These things are low power. That's what we say. But then we say we connect them to the internet and they're going to communicate all the time. I'm like, this does not make any sense, people. Who came up with this name called IoT? Right? So now I kind of like to say it's really about intelligence on things. Makes much more sense, right? But nonetheless, this communication loop, even if you turn it into this intelligence of things, suffers from the feedback loop thing.
Right, no, that makes a lot of sense. Although I also think that there's a kind of potential distinction between, again, IoT kind of situation and let's say wearable devices kind of situation. You made an example of the Apple Watch, for instance, and I think that could be, putting that into perspective, right?
Yeah.
So speaking of this, these topics, there were a couple of questions in the chat that I thought were really relevant from both Chuck and Crazy Boy. Do you have any thoughts on kind of continuous learning in TinyML or on-device learning adaptive models? It seems like right now the paradigm is train somewhere and then try to put it onto the TinyML. Do you think there could be a paradigm shift there anytime soon?
Anytime soon in practical kind of overall, I mean, obviously there's research on it, but that's a long ways out still, right? Like in a practical sense, I think it's still a little ways out, because it's nice to be able to say that these, you can train the models and whatnot, but in a serious pipeline, if you actually think about it from an MLOps kind of a perspective, right? The notion that these models are continuously learning and doing something a little different is actually intimidating for anyone who's actually deploying anything at scale. Because how do you monitor and maintain that guarantee of quality, right? As it is, you already said we're going to have concept drifts already that are an issue for us to deal with, right? And then on top of all that kind of drifts, you're then talking about having these models becoming even more heterogeneous and so forth. So practically speaking, I think we're ways out from actually realizing that in production systems.
Gotcha. Theodore, do you want to go ahead?
Yeah, Vijay, I had a question in mind, and you might have partially answered it with your comment about Internet of Things. But when you were talking about the specialization of devices and heterogeneity in that space, I recalled, hearing about similar problems in another, ML frontier, which is federated learning. And then I started to think, is there any kind of intersection between these two at all? And I couldn't think of anything, partially because, as you mentioned, right, the communication costs are so high for these really tiny, tiny devices. And federated learning is very comm heavy. But I wanted to ask someone with more expertise in this area, do you see any intersection between TinyML and federated learning?
Yeah, I get this all the time. And I do conceptually, yes, right? Obviously, this is a great opportunity, a great avenue for federated learning, just because of the distributed nature of this whole thing. But I also struggle with it for the obvious reasons of, I don't know how effective this is really going to be. I mean, let alone the fact that you have communication and so forth. I think the other big problem that a lot of people have with that is the fact that you don't necessarily want to have like these models that are getting updated. Like people haven't quite figured out. It's exciting to say that these models are learning, but then it's very hard to have QA on top of them, right? That's a serious thing. You talk to companies, they'll say like, well, yeah, that's cute, but I'm not putting that out there because I don't know how it's going to behave for my customer, which means it'll come back and bite me. So I think like as much as federated learning is going wild and crazy, it's like wildfire out there. I think it's still got serious issues in terms of being able to get to TinyML kind of devices.
I wanted to switch tacks a little bit and talk a bit about that first challenge that you mentioned with just the heterogeneity of all the different TinyML devices. I was wondering, if you're developing TinyML systems or algorithms, is there any way to kind of account for some of that heterogeneity without just going on and kind of running it on the device itself? Is there, maybe space for simulation or anything like that? Or if you're in this space, is it really just the case you have to get the device and run it and kind of see what the characteristics are?
This is fundamentally speaking, this is not a new problem that's only come about as a result of these devices. So the first time we ever really got into this space was really when we had smartphones, right? Mm-hmm. Smartphones are inherently physical devices. So if you're talking about a lot of things like, AWS is like a device farm. Or you go to Google has a device farm for, running the code on a whole bunch of different devices, right? In fact, Facebook had a paper, Inference at the Edge, where they talk about like, if you look at the distribution of different kinds of smartphones that are out there, not everybody has an iPhone. Like the large number of users have mediocre phones, right? So you can't build some sort of super fancy model and stick it in that device and assume, oh yeah, it's going to run on this fancy accelerator that's on this iPhone or something like that, right? You have to cater for the fact that you have this mass heterogeneity, and so you try and normalize or reduce the performance expectations of the model so that it'll run okay on most of the devices. Now, to deal with that sort of an issue, that's pretty much the first time we kind of ran into this sort of a heterogeneity issue, because the smartphones are also extremely heterogeneous. And what we ended up creating is a lot of emulation mechanisms, emulators, and so forth. So for example, in TinyML, you can have emulators you can use. So something like Renode is a SOC level emulator that is a functional emulator of a whole device, right? So it's not timing related, it's more functional. So you can use those kinds of devices to test, do your CI/CD flows and so forth to actually test whether the application is going to work well, or, is it functionally okay on this particular device. Some of the problems we get into there is around the sensors, because all of this stuff is about sensors. Yes, you can emulate the sensor by feeding in fake data coming through, but then it's hard to kind of really you always have to have the data sets. And the whole problem is like, it's a chicken and egg problem. You don't have the data. There are no data sets really. I mean, I like to ask this question, what's the ImageNet of TinyML?
Right.
There is no ImageNet kind of data set. That's a killer data set. The closest you can say is maybe like speech commands. That's the closest. I mean, but even then, we all know that, even people say this, it is not as representative, which is why we created the multilingual spoken words corpus, because it has a lot of real noise and so forth in there. So there are mechanisms to kind of address this in part, but they're not as effective. I mean, I have talked to startup companies that actually do this, because I have an MLOps for scaling TinyML course that's actually coming out next month. And I was talking to a large number of companies, asking them, hey, what are some of the technical issues you face when you're actually trying to deploy these small models on various devices? And I was like, how do you do your CI/CD and all of these things? They were like, we plug the device in. And I was like, well, obviously you do plug it in. They were like, no, we physically plug them in. this thing is not as scalable as you think it is. It's not like, we have some sort of nice distributed operating system. You don't even have things like Android, which is a full-blown operating system where you can actually communicate things to it, push the APK, all those things. You have to tether them in. So it's very hard to scale things out. I honestly think that as much as there's a lot of excitement in the field, the opportunities are really around building the infrastructure that will enable people to actually deploy models easily and be able to have robust deployment strategies.
Gotcha. There were a couple of kind of slightly more technical questions in the YouTube chat I wanted to get to. So one comes from Mi Jung, who's at Michigan State and was actually a guest on our podcast. Do you think AutoML has any role in kind of realizing solutions for TinyML? And then another question comes from Chuck. What do you think of MATLAB coder types of frameworks where you apparently you can generate C or C++ for a desired embedded system?
Yeah, very good questions. Yes, the AutoML path, the AutoML path is almost a necessity in this space. A lot of startup companies, if you go and talk to them in the TinyML thing, you will find that they tend to have some sort of AutoML pipeline integrated in there. And the reason is exactly because of the damn heterogeneity, right? Many of them will tell you hands down, they're like, there is no way our ML engineers can support the number of devices that we have to look at, right? And the number of devices means you have all this heterogeneity again. It's like, it's impossible to get that low performance or having that extremely shrunk down model. And it's nice, right? Because AutoML, the design space, when you're looking at these TinyML models, is really not that large compared to traditional kind of, very large networks, right? The hyperparameters are largely around feature engineering aspects, your sensors and your hyperparameters around your sensors and the amount of feature engineering you're going to do on the input stream that comes in. And then some number of hyperparameters around what the microcontroller's characteristics are, right? So it's fairly restricted. And this is why I think like a lot of startups actually see a lot of value add to be generated out of like, AutoML-based methods for this. Almost every company I know, almost every startup I know who's actually in the business of deploying models here does some sort of AutoML, because otherwise they just can't scale. They just practically, you can't do it. And then the second question about MATLAB style tools, I think, yeah, they're definitely increasing. There are companies like Edge Impulse and a couple others like SenseML and whatnot that are trying to effectively become the MATLAB version for TinyML, which is like make it very, very easy to deploy code where you focus on the high order task and whatnot. And then of course you can export it down to C, C++ libraries that get generated. The challenge that you will find, a lot of companies will again say this, because so much of it is tied to like these different kinds of sensors, and the sensors have very different kind of characteristics. They're struggling with building a general pipeline that works. So for most cases, what's actually happening is people will come up with some sort of pipeline and say, okay, yeah, like, if I'm looking at this type of time series data, or if I'm looking at this type of image data or sound data, you can create stock pipelines. And that's what a large number of the startups are actually doing right now, right? Really nice push button solutions. But when companies or when users have a need for a solution that doesn't quite fit into that template, you're out of luck. And again, it goes back to the same issue that this is really fragmented space. Fragmented, or you could say like it's just a very broad space. So it's hard to build, a single tool that can do it all. In fact, if anyone said that, I'd be like, you're blowing smoke.
Gotcha. Great answers, Vijay.
Do we have other questions up here? Do you have a question? I think you.
No, sorry, I wanted to, double click on just this aspect for a second. Like, I'm curious, Vijay, regarding the broadness, and I'm not super familiar with the space, but do you think in the future will increase even more, or there will be like a more, there will be consolidation in terms of the different architectures and the different types of systems that people will deploy on?
That's actually a very good question, one that I had not thought about. This is just my gut instinct kind of reflecting. I think we've seen this happen, in all honesty. We've actually seen this sort of bifurcation, like this mass heterogeneity happen and then fold back into very small number. A concrete example of this is really in the smartphone ecosystem. In fact, I had actually written a paper analyzing this because I've taken historical data for some other reasons, where I looked at the number of different chipsets and, when the smartphone ecosystem was booming, a large number of companies got wickedly excited and started doing all kinds of, SoC designs for them. But then now, if you kind of look at the number of companies that are really left in space, it's a handful, literally like 4 or 5, major companies that build the chipsets. And this is because the margins are really low, right? This got nothing to do with technicality. It's just, basic economics, right? So the margins end up being low. What that means is that you very quickly, have companies kind of falling off left and right from having this sort of ability to create it. And in fact, even within major companies like Qualcomm and whatnot, if you look at their SoC portfolio, they started to kind of clean it up a little bit, to tighten it up, because it becomes a major nightmare for these companies to actually maintain so many different chipsets, because then you get out to support them and so forth, right? Because it's not about just having a chipset. We all know that a chipset is a dumb chipset. It's a software that actually sits on it that actually makes it useful. And so having a broad heterogeneity didn't work in the ecosystem. And even though it's still very fragmented, the diversity has really slimmed down, relatively speaking. And I think that exact same thing is likely to happen, I would think, in the embedded ecosystem, because people increasingly will want the nice portability and so forth. But that's just my guess. I'm not saying this based on any sort of industry reflections or anything. I don't have data on it.
Certainly better than any guess that I could get. So that's perfect. Thank you very much for your answer, Vijay.
I think we're a little over the end of time, so I'm just gonna call it here. Thanks so much, Vijay, for answering a ton of questions, both technical and generally about this area. Very exciting stuff, and hopefully we'll start to see more of this get deployed. And really excited to see your work here in the future as well. I want to thank everybody who tuned in on YouTube and in the audience. Go to our website, mlsys.stanford.edu. You can sign up to our mailing list. We send out weekly reminders about talks that are happening, as well as subscribing to our YouTube channel so you can see the upcoming talks. I believe next week we have...
Next week we've got Shruti Bosale from Facebook/Meta talking about scaling multilingual machine translation to thousands of language directions.
Okay, awesome. Thanks so much, everyone. See you on YouTube. Bye.